minimize the bit error rate. And actually, this is one of the important performance metric in wireless communication. Suppose, for example, we can consider OFDM system, or we can consider maybe NOMA system, or EFMC, or GFDM, or any 4G MIMO system, or LTE system, long-term evaluation. For any system is considered before start researching. So first to calculate system performance. System performance means SNR versus BER. So with the help of different digital modulation techniques, BPSK and higher order modulation, QPSK, 4 QAM, 8 QAM, 16 QAM. So to calculate performance of system like OFDM system or a MIMO system, SNR versus BER. So first to verify the system performance, and always its a bit error rate will be minimized. And next, actually BER is in all 4G and beyond 5G wireless communications. So the bit error rate is one of the important performance metric. And next one is minimize required systems bandwidth. So actually already I told you the bandwidth is very costly or expensive. So that's why the utilization of the bandwidth is effectively utilized, because we are not using more bandwidth. Suppose, for example, if the more data is transmitted and increase the more bandwidth, that is not the like a goal. So to whatever bandwidth of the channel has given, or whatever bandwidth has given, for a given bandwidth we can transmit more data. So the minimize the system bandwidth. So that is important. So we are not wasting any bandwidth. So for a given transmission bandwidth, or for a given channel bandwidth, and how the more data is transmitted is the important. So that's why I will show you one slide whether the bandwidth is increased or decreased by sending the information or by sending the symbols. So this is minimize required system bandwidth is one of the design goal in communication system. So this minimization of the bandwidth is in the 4G and beyond 4G applications. So this is one of the important performance metric. And next point is to minimize system complexity. So the overall system complexity is reduces, not increasing the system complexity. Actually, when we compare it to 4G wireless communication and 5G wireless communication, one of the major differences in the 4G, there are many drawbacks in 4G, but one of the uh, drawback is compared to 4G, 5G, and 5G to beyond 5G is actually in the 4G wireless communications, PAPR is more, especially in OFDM. That is one of the drawback. So that drawback is eliminated. We go for some PAPR reduction techniques. So with the help of the PAPR reduction algorithms, to reduce the peak to average power ratio. But complexity, when 4G is compared to 5G, it's one of the drawback in 4G. Not only PAPR, other drawbacks are also there. But compared to 5G to beyond 5G, or compared to one 5G system to another 5G system, one of the drawback is complexity. Suppose, for example, the one example of 5G wireless waveform is UFMC is the 5G waveform, and FBMC is the 5G waveform, and GFDM is also 5G waveform. NOMA is 5G and beyond 5G. So when we compare it to GFDM, FBMC, and UFMC, the system complexity is very high, because in that system they are using filter banks. Bank of filters are used. whereas in the NOMA system, we are not using bank of filters. So the system is a very simple NOMA, but NOMA is 5G and beyond 5G system. Especially in the 5G systems are GFDM, FBMC, and EFMC are 5G systems. In the 5G system, one of the drawback is complexity. So to reduce the complexity of the 5G system, we go for the NOMA system. So that is in this point, like in this design goal in communication system, the research area is like when we compare it to the 5G and like another 5G system is NOMA is the to reduce the complexity of the system. And so the overall, and another example is, suppose for example, MIMO and massive MIMO. So in the MIMO system, the overall system performance is increases, or the transmission rate is increases, spectral efficiency is increases by increasing the number of transmitting antennas and receiving antennas in the MIMO system. So number of transmitting antennas and receiving antennas are increases means at least minimum 64 transmitting antennas and 64 receiving antennas, then only the system is called it as massive MIMO system. In the massive MIMO system, the minimum 64 transmitting and receiving antennas are used. So if number of transmitting antennas are increases, the performance increases, but one drawback is complexity of the system. Because if more number of transmitting antennas, each transmitting antenna is having some power amplifiers, RF amplifiers, some electronic circuit inside the each and every antenna. So the each and every antenna is dissipate even in the power also. So that's why the overall hardware complexity is increases by increasing the number of transmitting antennas. So that's why always it's minimize system complexity. Actually, this is one of the R&D problem or a research problem. And finally, the last design goal in communication system is to minimize required power. So how to power is reduces or minimize the transmitted power. Even in the power is also very costly. We can't use more power to transmit more information bits, or the it is not easy to increase the uh, power, because the power is also a costly parameter. So that's why to reduce the transmitted power and transmit the information symbols. Actually, these are design goals in wireless communication system. Maybe if we want to increase the complexity, if the complexity is increases, we are compromising this parameter, and our aim is only increasing the transmission rate. Maybe some goals we can achieve, and some other goals are maybe other problems are also arises. So that's why there is a trade off in between the parameters. And coming to in any wireless communication engineers, so their design effort is to high energy efficiency and high spectral efficiency, even in 4G to 5G, 5G to beyond 5G. The important performance metrics are not only energy efficiency and spectral efficiency, like so what is the latency, and what is the transmission rate, and what is the gain, and clock frequencies. So there are some, like what is the PAPR, and like there are some parameters, design parameters. Especially generally, energy efficiency and spectral efficiency is increased, and reliability of the system is also increased, and the system circuit or a design of a simple circuit, both at a transmitter side and the receiver side. So the designers trade off among above parameters to meet a design goal. Just I am concentrating these two important design goals. One is energy efficiency, and second one is spectral efficiency. I am concentrating only these two parameters. What is meant by energy efficiency and what is meant by spectral efficiency. So, the energy efficiency is defined as the number of bits transmitted per joule of energy. Like, what are the units of energy efficiency is bits per joules. And spectral efficiency is the information rate that can be transmitted over a given channel bandwidth or over a given bandwidth in a specific communication system. So the units are bits per second per hertz or the spectral efficiency. So these two are important designed parameters in our lecture. So energy efficiency versus spectral efficiency. However, if any system that designed was energy efficient, it must not spectral efficient. Suppose, for example, when that our designed system is a energy efficient system, definitely the spectral efficiency will be decreases. Suppose if we want to increase the spectral efficiency, the energy efficiency is also decreased because these two are inversely proportional. One is increased and another one is decreased. So there has been a trade-off between energy efficient and spectral efficient communication system designing. So this trade-off had been removed according to this, according to this lecture or according to this research paper, by using spatial modulation MIMO scheme instead of conventional MIMO scheme. So in the conventional multi-input MIMO is one of the multi-carrier system. When we compare it to the conventional MIMO system, compare it to the spatial modulation MIMO scheme, so there is a trade of being removed, because removing means if the system is a spectral efficient and energy efficiency is not decreased, we are at least trade off in between spectral efficiency and energy efficiency. So what is the fundamental relation between energy efficiency and spectral efficiency? So this equation is applicable over AWGN channel. If we go for fading channels, this equation may not fit into the fading channels. So this is applicable only over AWGN channel. Energy efficiency is equal to spectral efficiency times of N naught into 2 power eta SE. SE is the spectral efficiency, E is energy efficiency, minus 1 inverse. So this is the relation between energy efficiency and spectral efficiency. So how I have written this equation, I will show you simple mathematical derivation. This is 2-3 steps only. So C is equal to, this is the capacity of the channel over AWGN. C equal to B log base to 1 plus P by N naught B, where P is the signal power and N naught B is the channel noise or noise power, and B is the bandwidth of the channel, and C is the capacity of the channel. So spectral efficiency is equal to C by B. So what is C by B from the above equation? C by B equal to remaining equation, log base to 1 plus P by N naught B. So this can be written as 2 power eta SE 1 plus SNR. This is SNR. P by N naught B equal to SNR. So again, to rewrite this equation, 2 eta SE minus 1 is N naught B is equal to P. And what is energy efficiency? C by P is the energy efficiency. So C is equal to eta SC into B. This is C equal to B into eta SC. B into eta SC. And P is equal to, this is the equation P. 2 power eta SC minus 1 into N naught B. B cancel. Eta SC by N naught into 2 power eta SC minus 1. So this equation can be written as eta EE equal to eta SC into, actually N naught into 2 power eta SC minus 1 inverse, because here it is having in the denominator. So in this equation it can be written as eta SC in multiplication inverse. So this is the relation between energy efficiency and spectral efficiency of wireless communication system over AWGN channel. So fundamental trade-off between energy efficiency and spectral efficiency, where N is the, sometimes they have written capital N and small n also, where N is the receiver noise, power spectral density, and it was clearly seen from the formula that if we increase the spectral efficiency, it will decrease the energy efficiency. So already we have discussed in the previous slide, spectral efficiency increases means automatically the energy efficiency will be decreased. As spectral efficiency increases to the power base 2 will increase, because in the previous equation. So based on this equation, we can tell spectral efficiency is increases, energy efficiency will be decreased. Our energy efficiency will be increased and spectral efficiency will be decreased. So what is the fundamental, or what are the fundamentals of multi-input and multi-output system? In MIMO scheme, we use multiple antennas at the transmitter and receiver, because why I am talking about MIMO system means index modulation is first introducing in the MIMO system. Later we can introduce in the either it is a OFDM system or 5G system and beyond 5G system, even in the UAV SM also. Drones integrated with any wireless communication system like 4G or 5G. So even in our drones also, drone is considered as a base station. In the base station, so how it is integrated wireless and UAVs, and how it is incorporated index modulation techniques. So that's why first I will discuss some basic concepts of MIMO system. Later, index modulation concept I will discuss and give examples also. In MIMO scheme, we use multiple antennas at the transmitter and receiver, which are active simultaneously for the transmission of modulated signals. So we have to use multiple antennas and multiple antennas at the transmitter side and receiver side to increase the spectral efficiency. So the purpose of increasing spectral efficiency has been increased, but energy efficiency on the other hand is greatly neglected. So suppose we want to increase only spectral efficiency and neglecting the energy efficiency in MIMO system, but in other multi-carrier systems not like that. So if we want priority for both parameters, spectral efficiency and energy efficiency, how it is trade in between spectral and energy efficiency. And coming to what is the difference between spatial diversity and spatial modulation or multiplexing. Spatial diversity and spatial multiplexing. So the spatial diversity is, suppose here we have one MIMO system, 2 by 2 MIMO system. So from the transmitter side we have two transmitting antennas. From the receiver side we have two receiving antennas. So from transmitter side we are transmitting two symbols, symbol 1 and symbol 0. So maybe if each symbol it contains so more than one binary information. When symbol 1 and symbol 2 was transmitted by the transmitted from the transmitter side using a spatial diversity concept, symbol 1 is transmitted by transmitting antenna 1 and the same symbol is transmitted by transmitting antenna 2. So symbol 1 and symbol 2 both are transmitted by the same different antennas, antenna 1 and antenna 2. And the symbol 1 is transmitted from antenna 1 to the receiving antennas. There are two multiple paths. And similarly, from antenna 2 is transmitted by symbol 1 and received at the receiver side by two multiple paths. R1 and R2 are the receiving antennas. And what is the receiving and received signal? So here there are two symbols, and similarly, if one symbol is transmitted and received at the receiver side, next symbol 2 is also transmitted by both antenna 1 and antenna 2 in the spatial diversity concept. Whereas in spatial multiplexing is, this is the spatial multiplexing block. Here same as in the previous spatial diversity concept, we are transmitting two symbols S1 and S2. Symbol 1 is transmitted by transmitting antenna 1 and symbol 2 is transmitted by transmitting antenna 2. In the spatial multiplexing, because in the both the 2 by 2 MIMO systems both are in the same 2 by 2 MIMO system, but in the spatial diversity, at a time, the transmitting antenna 1 and 2 both are transmitted by the same symbol. Whereas in spatial multiplexing concept, the symbol 1 is transmitted by transmitting antenna 1 and symbol 2 is transmitted by transmitting antenna 2. So at a time we are transmitting two symbols here. Whereas in spatial diversity, at a time we are transmitting only one symbol. So the transmission bandwidth is for a given transmission bandwidth. Here two symbols are transmitted. Here at a time only one symbol is transmitted. At a time one means the bandwidth requirement is more in spatial diversity and the requirement of bandwidth is less when compared to the spatial diversity. Here it requires less bandwidth, and using in the spatial diversity it requires more bandwidth. So because this is one of the drawback in spatial diversity, because it requires a more bandwidth to transmit the information. But coming to the spatial multiplexing, it does not require more bandwidth of the channel. Over the given channel bandwidth, we can transmit more information. So that the bandwidth, wastage of the bandwidth is also reduces using in the spatial multiplexing concept. And coming to using spatial multiplexing concept, there are two symbols. If this symbol 1 is transmitted by antenna 1 and symbol 2 is transmitted by antenna 2. So there are in here two multiple paths when symbol 1 is transmitted and symbol 2 is transmitted, where H11, H12, H21, H22 are the channel coefficients and R1, R2 are received signals. So R1, R2 is equal to, the channel matrix is H11, H12, H21, H22, where S1 and S2 are the transmitted symbols. So the received signal equation is, in any wireless communication system, Y is equal to Hx plus N. H is the channel coefficients and Hx or S is the transmitted symbol and N is the channel noise and R is equal to received signal equation. So R equal to Hx plus N or Hs plus N. So the sizes of R, because if it is a 2 by 2 MIMO antenna system, The received signal dimensions are 2 by 1 matrix, and the channel matrix is 2 by 2, and the transmitted symbol matrix is 2 by 1, and AWGN channel noise is 2 by 1. How MIMO is not energy efficient? So MIMO is not energy efficient because when multiple antennas will active, they will dissipate energy. As every antenna consists of circuit of RF amplifiers, operational amplifiers, and power amplifiers, which required power to run and dissipate the energy. Suppose what is the massive MIMO system is multiple transmitting antennas and multiple receiving antennas. So each and every antenna it consists of RF amplifiers, operational amplifiers, and power amplifiers, which requires power to run and dissipate energy. So in case of MIMO, when multiple antennas work at a time, so all the antennas containing circuitry inside them and in working condition and will dissipate energy. More the number of antennas, more is the dissipate energy, because if each and suppose in the uh, spatial diversity, if both antennas are in active, if both antennas are transmitting the same information, so the bandwidth is the wastage, and also the same information is transmitted by the two antennas, and antenna 1 is active and antenna 2 is also active. If antenna 1 is active means what is the hardware circuit inside this antenna? Some power amplifiers, operational amplifiers, and there are some electronic circuit in that antenna. So if the once the antenna is active means, so it is required power to run the antenna and dissipate energy. So if the two antennas are active, if the two antennas dissipate power to run and dissipate the energy efficiency will be decreased. So in case of MIMO, when multiple antennas work at a time, because this is the simple MIMO system 2 by 2, we go for the 4 by 4 system. Four antennas are active and four antennas are transmitted by the same information. Whereas in receiver side also, it's a four receiving antennas. So in case of MIMO, when multiple antennas work at a time, so all the antennas containing circuitry inside them and are in working condition and will dissipate energy. So the energy efficiency or energy dissipate energy is more. So once the dissipation energy is more means the system is not a efficient or energy efficient system. So that's why in the conventional MIMO system, if all transmitting antennas and receiving antennas are in active, if it is active, they will dissipate energy and energy efficiency will be decreased. So more the number of antennas means in the dissipate more energy. So as we did not decrease the number of antennas because it will decrease the spectral efficiency. We want to increase the spectral efficiency is our aim. So we cannot to decrease the number of transmitting antennas. If number of transmitting antennas are increases, and overall system performance is increased. But the drawback is if all transmitting and receiving antennas are dissipate energy, so the energy efficiency will be decreased. So we are not decreasing the number of transmitting antennas. How to increase the energy efficiency is the solution of MIMO system, and this solution is achieved by using the index modulation concept. So once again I will repeat, in the MIMO system, conventional MIMO system, If we want to increase the spectral efficiency and data rate is increased, the number of transmitting antennas are increases. Once the transmitting antennas are increases, each and every antenna is it dissipates some energy. So the overall spectral efficiency increases, but energy efficiency will be decreased. So the initial proposed solution is, but solution is decreasing the antennas if a number of antennas are increases and increases spectral efficiency and decrease the energy efficiency. So simply to increase the energy efficiency and not only decreasing the antennas is not the correct solution. So the initial proposed solution to increase energy efficiency was to decrease the number of inactive elements. So this was done by monitoring the power of active antennas which they are receiving. The antenna receiving less power will be shut down so that the power dissipation will be decreased. It is clearly understand in the further slides. So, what is the solution? How to energy efficiency will be decreased because increasing the number of antennas. Increasing the number of antennas, the spectral efficiency is increased and only energy efficiency is decreased. So, without decrement of the energy efficiency, we can increase the even in the energy efficiency without eliminating the number of transmitting and receiving antennas without reducing the antennas but with increase the energy efficiency. What is the solution is called as a index modulation technique or spatial modulation is one of the index modulation technique. So there are some different types of index modulation techniques. One is spatial modulation, and second one is quadrature spatial modulation, and the third one is generalized spatial modulation, and the fifth one is multiple antenna, or a group of antenna system, and another one is suppose if it is generalized. There are, if we know the spatial modulation concept, the same concept is extended. We go for the QSM and we go for the GSM and so on. So in the spatial modulation is one of the index modulation technique. So in the spatial modulation, MIMO was proposed solution which will not only increase data rate but also increasing energy efficiency. So actually not only increasing the data rate, not only increasing the spectral efficiency, but it is also but it is also increase the energy efficiency and spectral efficiency is the solution of spatial modulation MIMO system. In spatial modulation MIMO, it will remove this trade-off by using only one active antenna. What is the concept of spatial modulation is only one antenna is active. Suppose we can take 2 by 2, 4 by 4, 8 by 8, 16 by 16 antennas. Out of like 4 by 4 antenna, just for example, but all four antennas are not in active. So, in the spatial modulation concept, the first point is only if we can take n number of antennas, but only one antenna is active at the transmitter side and the receiver side. So, only the remaining three antennas are in inactive mode. So, this is the concept of index modulation because in the spatial diversity, all n number of antennas are active to transmit the information. Whereas in spatial modulation concept, only out of n number of antennas, only one antenna is active. In between the transmitter and the receiver, we are having one switch. So that is called as a RF amplifier. So how only one antenna is used and transmit the entire information so that it can be explained clearly. And mathematically, whether the energy efficiency is decreased or increased, we can see in the further slides. In SMIMO system, spatial modulation multi-input multi-output system, how SMIMO will be feasible? Minimize the number of active antenna elements in order to increase the energy efficiency by reducing the circuit power consumption at the transmitter. Given the implementation and size constraints, maximizing the number of passive elements in order to increase both the spectral efficiency and energy efficiency by reducing the transmit power consumption. So the passive elements are the elements which does not require any power to work. So what is the formula for the spectral efficiency of spatial modulation? The spectral efficiency of spatial modulation is maybe some textbooks they have written, or some textbooks eta is the notation of spectral efficiency of a spatial modulation, log base to m plus log base to nt. This is the mathematical formula for spectral efficiency of SM modulation technique, where M is capital M is modulation order, and log base to NT is number of transmitting antennas. So actually I will stop it here. Next, tomorrow I will continue the how to calculate the spectral efficiency, what is the importance of this efficiency, and how to calculate, like how to increase the information rate, and bandwidth it cannot be increased, and even in the energy efficiency is also not like degraded by reducing the number of transmitting antennas. So next class, sorry, next means next lecture, tomorrow's lecture, I will continue the same topic. Any doubts regarding up to this? Nageshwar Rao?
Yes, madam. Participants, if you have any doubts, please ask. Madam, yes, they are not responding. You may not have any doubts.
Okay.
Thank
So,
you, madam. Thank you for your wonderful
Nageshwar Rao,
session.
Nageshwar Rao.
Madam.
So one of the student has written one doubt.
Yes,
Can
madam.
we use diversity, MRC, EZC is used to increase the spectrum utilization?
Yes, madam.
So actually diversity techniques are used to combat the fading effect. To reduce the fading effect, the signal strength will be increased. So actually diversity techniques are used to, it is not utilizing the spectrum, or spectrum is not effectively utilized, but they are used to combat the fading effects or reducing the fading effects by using the diversity techniques, and to combat or to reduce the intersymbol interference by using the equalization techniques. Okay, Nageshwar Rao.
Madam. Thank you, madam. Thank you for your wonderful session.
Okay.
And next session will be going to start right now. Already resource person has joined. So this session is handled by Dr. Saurabh Solanki, Assistant Professor, Department of Electronics and Communication Engineering, NIT Warangal. Dr. Saurabh Solanki received his MTech and PhD in Electrical Engineering from Indian Institute of Technology, Indore, in 2015 and 2019 respectively. From 2019 to 20, he served as a research professor at Korea University, and where he has been awarded Brain Korea 21 postdoctoral fellowship. And between 21 to 23, he worked as a research associate at the Interdisciplinary Center of Security, Reliability and Trust, University of Luxembourg. Since 2024, Dr. Solanki has been serving as assistant professor in the Department of Electronics and Communication Engineering, NIT Warangal. He has research interests includes terahertz communication, non-terrestrial networks, cognitive radio, green communication, and physical air security. He is received an exemplary reviewer award for IEEE Transitional Communications in 2020, and he has co-recipient of the Best Paper Award at the International Conference on ICT Convergence, South Korea. Dr. Solanki has an active senior IEEE member. He has served as a technical program committee of several international conferences and regularly contributed as a reviewer of major IEEE journals and conferences. He is currently serving as a associate editor for the IEEE Communication Letters. SAR has published many research articles. In most of the research articles in the IEEE transactions and IEEE related journals, SAR has vast experience in the UAV non-terrestrial communication point of view. So the participants may gain more knowledge in this session. I welcome Dr. Saurabh Solanki sir to take over the session.
Thank you, Nageshwar, for the introduction. First of all, am I audible properly?
Yes, sir. Yes, sir. Audible, sir.
Great. Then I'll first switch off my camera, then go ahead with sharing the presentation. Can you see my screen?
Yes, sir. Visible, sir. It is visible.
Okay. So good afternoon, all the participants. I welcome you in this wonderful FDP, which is based on UAV. I hope we are able to impart knowledge and do you some. I hope you can have lots of takeaways from the talks which you are going to have under this FDP. So as to this topic, this talk is about the non-terrestrial networks, and we'll see it from the perspective of 6G wireless communication. What role the non-terrestrial network is going to play for 6G wireless communication? That will be our agenda, and then we'll highlight some. Okay, so here's the broad agenda which we are going to see. So first off, I'll start with the introduction. In the introduction section, I'll talk about what is this 6G about, what is this buzzword, when is the expected timeline about this deployment of 6G. Then we will talk about various architectures of NTN and see them from standardization perspective. Then I will also highlight some research challenges. We'll keep those research challenges pertinent to the UAV context. And then I will go on to explain some solutions as well, which we have done to address certain challenges. And then I will end my talk by highlighting some potential research directions. So first of all, just to give you the context, why we have been evolving over generations and generations. So we started off with 1G, 2G, 3G. Currently, most of us are using the 5G. Then why is the need of this 6G wireless communications? Where do we lack that we need this 6G wireless communications altogether? So to put that in perspective, I want you to have a look at the statistic which I'm showing on this particular slide. So here, so if you see this bar plot on the left, so it shows about the internet penetration in India. So the y-axis shows the internet penetration rate in percentage term, and x-axis shows a gradual evolvement starting 2014, and this data is as of 2024. So basically on x-axis you'll see the years. So gradually over the years how the interpenetration has been grown. So if you see this first, so as of 2014, the internet penetration rate was about 13.5%, which was very low. But then we have seen around that time the advent or the onset of Geo, right? So Geo has launched their breakthrough services through Volt services, that is LTE, which we are using these days. So Geo has launched this Volt services around 2014, and since then, and the Geo, what remarkable thing which Geo has done, they have provided this data access or the internet access to all of us in very cheap rate. So they have made it so cheap that the internet penetration since then has grown exponentially. So if you see then fast forward it to 2024, that's the remarkable progress. In 10 years from 13.5%, we have reached to almost 53%, 52.4% to be precise, as of 2024. And as we speak today, this maybe this number has grown further. And the same trend can be observed in the right side of the plot. And this data stands for the world. So in the left, we are talking about this, we are just seeing the internet penetration from the Indian perspective, and towards the right, we can witness the same trend. So globally also roughly, so here the axes are a bit different. So in y-axis, we have number of users in millions, and x-axis is the years, gradual progression of the number of years over the years. Okay, number of users over the years. So as of 2005, there was around 1,000 millions of users who were using the internet, and as of 2023, this data is a bit old. So it's still 5,400 millions of. So roughly, this also translates to around 50% of the world population. So this data tells us that around 50% of the population had access to the internet. So although it's good that we have progress, we have made a progress, and that too exponential progress, but on the flip side, if you see it, still glass is half empty. So around 50% population still does not have access to the internet, and therefore this technology is constantly evolving to find the ways so that we can reach the last mile of the world, where traditionally we have not been able to reach. So why this 50% population did not have access to the internet? There are multiple reasons. One of the reasons is that there are because of the demographic challenges. For example, where the terrains is very difficult. For example, mountain, hill regions, deserts. So there, the deployment of traditional terrestrial infrastructure is very difficult, and therefore it's not just some visibility hurdles which have stopped us. Some things are naturally hurdled, which have stopped this internet penetration. So this is the main motivation behind this non-terrestrial network, which is coming into the signal. So the objective of non-terrestrial network is to provide ubiquitous connectivity or global connectivity across the world so that we can increase this internet penetration rate further. Ideally, we want to make it up to 100. I don't know how long it's going to take to reach us there, but that's the target. Now, what is 6G? We have been seeing the evolution of mobile phone or wireless communication or cellular communication in our. So we started off with 1980 with 1G, first generation of wireless communication. So first generation of wireless communication were able to offer us the data rates in order of 2.4 kb. Then came along 2G. So 2G, with 2G, we were able to get the speed up to 64 kbps, and 1G was limited to voice services. But with 2G, we were able to transmit some amount of data in the form of SMS, short message services. Then with 3G, we have been formally or connected to the internet, which means now with 3G we were able to connect anyone across the globe. That that's when we were really connected to the internet. So up to 1G and 2G, this was more of a local services. So the 3G, with the advent of 3G, we were truly be able to communicate across the globe. And the data rate were still limited to 2 Mbps. So to see this today, if you compare this data rate as to what we are getting today, it feels nothing. But at that time, it was a truly evolution or revolution rather. Then and on the x-axis you can see the timeline, and the timeline in of deployment of these technologies in India may be a bit different, plus minus 3-4 years, but this is roughly as per the standards, the global standard. Then 4G globally came around 2010, and in India we have truly seen it around 2014 and 15. So the 4G was able to offer us a remarkable speed that is about 100 to 1000 Mbps, and that has transformed many technologies and gave rise to many new applications. At that time, we have seen new phones coming up, Android, and they had this different applications, gaming, streaming websites. Now, because why they became popular? Because this large amount of data gave rise to many new applications which were traditionally not possible because of the lower data rates. And around 2020, we have 5G, which was deployed commercially around 20. In India also, I think we have deployed it in some cities around this time. But now we are also venturing into tier 2, tier 3, tier 4 cities. So more or less, all of us are also probably using the 5G if you have the phone compatibility. Now, this was the evolution until 5G, which we have seen. And 5G, most of us are using it. Now, what about the 6? So we have been seeing also the applications, how they are evolving. So in 2010, we have seen a lot of applications. And then with 5G, we talked about Internet of Things. So before that, we are just talking about the applications. Now, but with 5G, we also talk about the internet between the things, not just human. Before this, only humans were connected to the world or the internet. Now we have with this IoT, we can talk about the Internet of Things. Things can also form their network. Then we can just make them smart. And with 6G, we are talking about towards a fully digital and connected world where humans, things, and all the layers in the network, they are fully connected. So essentially, 6G will contribute to fill the gap beyond 2020 society. So what 5G was not able to do, the 6G is expected to do all that. So basically, all our needs, basic needs, are satisfied with 5G. Our life is good. Our life is almost, now we are from different parts of India. We are able to seamlessly talk. We are able to discuss. We are able to attend these talks and presentation. So internet-wise, more or less, our demands, our basic needs and demands are satisfied with 5G. And still, what speed we are experiencing in the phone, that is not true 5G. So true 5G is still gonna take time, because the true 5G usually operates in FR2, that is frequency band 2. But still, whatever 5G signal which we see in our phone, that is 4G spec. So although some RAN technologies are different, but still we are spectrum wise, we are not utilizing the new spectrum. Still using the spectrum which was meant for 4G. So there is an overlap between 4G and 5G spectrum. And that overlap is also essential because we don't want a disruptive change. For example, if suddenly some operator has launched 5G, then those MNOs or network operators, they also want the existing users to continue use their new services. And therefore, though you need new phones to access the 5G, but that will not stop you to continue using the 4G network. If somebody does not have 5G phone, they can continue to use the 4G network. It's not like the 4G has been scraped off. That's how the gradual development works. And the timeline for 6G is about the globally across the globe, the companies, the industries, the governments, and the academic institutions, they agree on a common timeline, which is around 2030. So at least the commercial, this 2030, by that What I mean is it's the commercial deployment on the ground. The testing and everything has been done by that. But it may be a few more years, 3 4 more years, when we see the widespread use of this 6G amongst the public. So 6G will be basically about more about the quality of service rather than essential. There we have, we'll talk about the robotics, autonomous robot, augmented reality, virtual reality, autonomous cars, robotic surgery, and so on. So that will be just quality of life. 6G will enhance quality of life by posing different new application use cases, and which may not know as of yet. There can be also new use cases which will come later after the evolution. Now 6G, what is 6G? Nobody knows. So these government bodies, research institution, the company, they they provide their vision as to what this technology can be. So so now we'll see from different lenses of the from different perspective of the companies how what do they think about this 6G. So in this particular slide, I've taken this snippet from a document called as Bharat 6G Vision. So this is a 6G vision of our Bharat. So as per this document is free to read. You can just Google it and you'll find a nice PDF. And then you can read about all the 6G development, the technologies which are which are potential for to be deployed in the. Now, as per our Bharat 6G document, these are few requirements which 6G network has to offer, should offer. So the 6G network should ultra high bandwidth. So meaning high bandwidth means it is related to frequency. High bandwidth will be able to get only when we have new spectrum. Talk about new spectrum. So the 6G will explore new spectrum to offer the higher bandwidth, ultra high precision. So as we go higher on frequency, the localization, the lambda, the wavelength gets small. Smaller wavelength allows us for a high precision localization. And then ultra high performance, because performance is what we are aiming for. So performance in terms of everything, spectral efficiency, energy efficiency, the coverage, the throughput. Okay. And then ultra high intelligence, when combined with artificial intelligence, we want our network to be highly intelligent. Then ultra massive connectivity. So we want massive connectivity so as to fill that 3% gap. We want to ideally reach 100% of the population that can access the internet. And all this should be at lower cost and lower energy consumption, because also want these technologies to make sustainable, want to leave something behind for the future upcoming generations. Therefore, all the development should not be at the cost of environment. And therefore, the energy also, if you see, this is sustainability is also one of the crucial for any. It's not just related to wireless communication network. For any technology, these days the governments are emphasizing on the sustainability aspect of it. So all the development should be sustainable so that we can use them for hundreds of years in the future. And they also have to be affordable. India being a not so rich country, have to make this technological transition affordable so that poor of poorest can be able to afford. And then ubiquitous, it has to be everywhere. Ubiquitous means it has to be everywhere all the time. And these are some potential technologies which are also listed in this document, Bharat 6G Vision. So these are basically the enablers to achieve all this key performance indicators. So one is massive MIMO, use of massive MIMO. Another is artificial intelligence and machine learning. Then virtualization of the network. Then the non-terrestrial network. So the Bharat 6G document, it also emphasizes on the non-terrestrial. And this non-terrestrial network, it's an umbrella term. So as this FDP is UAV based, so UAV basically they are also under the umbrella of non-terrestrial. So anything that is not on terrestrial is non-terrestrial network. So UAV, as we know, they are aerial based network, air based networks. So they're also categorized into, they also fall into under the non-terrestrial network. So the 6G, this Bharat 6G document, it also mentioned about this HAPS and all the satellites, LEO, MEO, and GEO. And then this intelligence has to be, which will be facilitated using this AI. It has to be distributed across the network, not at centralized level or at a single node. The intelligence has to be distributed. Even your mobile phone, that should also be a AI capable, and that is called as AI native air interface. As per Samsung, Samsung has also laid down its vision about the 6G. So Samsung has talked about this performance indicator. Performance, this right to left has various performance indication. To start with, let's see this user experienced data rate. What data rate we as a user experience in our mobile, that is one of the KPIs, key performance indicators. This inner trapezoid, it shows where we are at 5G. And this point here, it shows where we want to be in 6G. So as per Samsung, currently we have this user experience data rate is about zero point 0.1 Gbps. This is an ideal condition. We will not experience this, but this is under ideal. So currently it is zero point 0.1 Gbps what can experience at the most. Now we want to increase it tenfold to 1 Gbps. That's the highly anticipated goal for 6G. In terms of energy efficiency, what is energy efficiency? Energy efficiency is how many data bits you can transmit in a given transmit power budget. More data you are able to transmit in a given transmit power budget, then better is the energy efficiency. So this is a relative term here. So in 5G, let's say if this is 1x, we want to double it. We want to achieve 2 times energy efficiency in 6G network. We want 6G network to be twice as energy efficient as 5G. Same goes for spectral efficiency. We also want this spectral efficiency for 6G network to double from where we are. And the latency, air latency, we want to reduce it by 10 times. So currently, the 1 millisecond is the targeted latency, and we want to reach at 0.1 millisecond. Latency is, you can see it's a delay between the signal when it leaves the transmitter, reaches the receiver. Basically, the delay that is quantified in terms of latency. Normally, we measure it in the millisecond. So, although 1 millisecond is also highly ambitious, and I think we still not could attain this, but nevertheless, these are just highly anticipated target. Even if we are able to, let's say, at 0.5 millisecond, 4 millisecond, that will be work. Next is the connection density. How many devices that can be connected to a network in a square kilometer region. So as of now, with 5G, we can connect 1 million to the power 6 devices in a square kilometer. Now we want to increase it 10 times to make them 10 to the power 7. We want to increase the connection density by 10-fold. And the reliability is the bits you're transmitting, whether they are being received at the receiver reliably or not. So, for example, the reliability of 10 to the power minus 5, this is where we are in the 5G. So, what does this mean, the reliability of 10 to the power minus 5? If you're transmitting 10 to the power 5 bits, then only one of them, chances of error is just 1 bit out of 10 to the power 5 bit. Okay, so that's why it is probability 1 by 10 to the power 5, making it 10 to the power minus 5. That's highly reliable, that is 5G. We want to further increase it 100-fold. Now we want the reliability of order of or minus. Meaning, if you transmit 10 to the power 7 data, 10 to the power 7 bits of data, only there should be chances of only 1 bit of error amongst those 10. That's the another. And the peak data rate over the network level should be 1000 Mbps. Sorry, Gbps, 1000 GB. Currently, we are at 20 GB. We want to increase it 50-fold. So 50 times, that's also a highly ambitious target. So this is the vision of 6G network. And on the right, there are different applications, the evolution of it. In 2020, we were just seeing the smartphones, and then with 2020, with 5G, we have seen the Internet of Things, gadgets, and then 2030 is hyper-connected world. Same goes for more or less all these different companies have more or less the same requirement. Maybe they differ on certain aspects, but they converge to the same central. So this document. This slide is as per the as per the vision of Nokia. So Nokia has also talked about different technologies. One is new spectrum, AI, common network as a sensor. If all your network is connected, hyper connected, then we can think of whole network as a sensor which is constantly sensing its surround. Then extreme connectivity. This is also similar to massive connectivity. And then cloud-based automated services. And then security, reliability, and all of this has to be extremely secure, because more the data, more the chances of data. And for this new spectrum, this 6G document from Nokia has also highlighted which new spectrum are we talking about. So these current 5G spectrum band on the list left cake, it's as per this. So this below is for the least pie of this cake is ranges from 600 to 2600 megahertz, and above this sits 2.5 to 4.9 gigahertz of the band. So this band is for the urban capacity, and this lower band is for wide area, because lower the frequency, the your signal can travel longer distance. And this is another 24 to 71 gigahertz band. This is also called as millimeter wave. This is for hotspot. When there is a hotspot, and if you want to deliver data in a smaller coverage region, for example, stadium, when there is a lot of crowds there. So this is higher frequency. We can't expect to have the higher coverage for this, and therefore this is limited to hotspot capacity. This band is also called millimeter wave band. And broadly, 5G, as per the 5G NR standard, we define this as FR2, frequency range 2, millimeter wave 2, and then this band is FR1. Below 6 gigahertz is FR. These two frequency band are as per the standard. Now, in 6G spectrum band, we will have all these bands, 24 to 7.1 gigahertz. Those are same as 5G spectrum. But now we have this additional spectrum band, which will be greater than 92 gigahertz, and that band is different companies call it different names. So here they did not, but then this band is called as terahertz frequency. Anything above 100 gigahertz is called as terahertz frequency. Point one, why terahertz? Because we can express the wave frequency in terms of tera. Tera is the order of 10 to the power minus 12. 100 gigahertz, 100 gigahertz I can express as zero point 0.1 terahertz. Anything above 100 gigahertz is terahertz. So typically 100 gigahertz to 1000 gigahertz, this frequency range is called as terahertz frequency. And this is the new spectrum which we may explore. We don't know whether we can achieve it or not, because this also comes with several challenges. Not simple that if there is high frequency, you can just go and use it. If it was so easy, why haven't we used it so? So there are certain challenges. Maybe we'll talk other day. That's beyond the scope of it. But that is Tera's communication. It has its own set of challenges. Now this timeline, I want you to show it from a 3GPP perspective. So this release document which you see, this release 16, 17, 18, 19, so these are published by 3GPP. So 3GPP is a standardization body which governs the regulations of telecommunications. So they publish this release document where they talk about all these development, the standards, and the protocols of different system aspects, RAN aspects, and link up aspects. So this with 2020 around 5G, we had this release 60. So the 5G, the discussion on 5G, the development on 5G was continued with release 16, and then with release 16 there was research started, especially in terms of test beds and prototyping and demonstrations. All that started with release 18, which was around 2023. There were some initial research work which also started before 2020, but those were just mostly theoretical. But the demonstrations and the test bed developed across the industry and academia, it started after release 7. That is to say, around year-wise, 2023. And currently, we are at release 19. So release 18 and 19, 19 is almost freezed. So release 16, 17 and 18, those documents are already freezed. And the work on release 19 will be freezed, I think, by end of this year or early next year. And with release 20, the 6G study will start. The true 6G study will start from the release 20 timeline. It goes by 2020, by release 2022. We are expected to finalize everything about the 6G, and then we can see. So once these standardization are formalized, then only we will see the commercial rollout of certain tech. And this is also 2030, the expected time. Now coming to the end. So now we have laid down motivation as to what is 6G and what are the underlying technologies that are there in 6G. NTN. What are NTN? NTN stands for non-terrestrial network. From its name, we can say that anything which is not terrestrial, they are non-terrestrial. In this slide, you can see that the NTN platforms include first, in the highest of the layers, satellites, which are in the space. So in satellites, we have different types of satellites: GEO, MEO, and three type of satellites. One satellite is called as geostationary Earth orbit, which moves in the geostationary Earth orbit. Another, they are also called as geosatellites. Another is medium Earth orbit. Another is low Earth orbit. For internet connectivity, which we are seeing, in fact, we are also using this now, internet-based, satellite-based internet. So for that, essentially, we use LEO-based satellites, because LEO are on the lowest of the space layers, and therefore the latency or the delay is less compared to GEO and MEO. After satellites, there are aerial platforms. So aerial platforms include your unmanned aerial vehicles, UAVs. They are also called as drones, and as per the standards, they are also called as UAS, uncrewed aerial systems. And then another category of aerial assets are HAPS, high altitude platform systems. So they are like the balloon, and they are not as popular as drones and satellites, but nevertheless, they are also listed as NTN platform. So what are the expectations from this NTN? So expectations from this NTN is they should be able to provide the ubiquitous. So wherever we can't reach terrestrially, the non-terrestrial network should be able to provide us the connectivity on those locations. Especially, for example, in the oceans, the maritime and aeronautical applications, the rural areas. Because in such areas, it is naturally difficult to deploy a terrestrial infrastructure. Terrestrial infrastructure is very complex. You have to lay down the fibers, and then you have to build a connection base stations which needs constant power supply. So all of this may not be possible in all because of geographical location. Other applications include the wide area content delivery, and then this is also one of the that why not from directly we can access the data from the satellite on our phone. So with iPhone 16, the Apple has provided this functionality, but that functionality is limited to SOS services. Only emergency you can transmit some signal, but can't use it for normal voice services and data services because you see the difficulty here is the propagation distance. For example, geo satellite, it's around 36,000 kilometers. So by the time the signal reaches, first it was heavily attenuated. Another is lot of propagation delay it goes, and therefore, as of now, it's not. We don't have the technology to support. Although it's this area is also in active area of research because phone has limitation of area. You can't build a dish size antenna. We are using it for TV, for movies, and then also for our broadband. But with broadband, you can have a larger dish antennas to receive the signal, which can amplify the signal, receive signal, because the satellite signals are weak when they receive on the receive. Therefore, given the smaller size of our smartphone, this direct smartphone access is still long way to go. As about the altitude, the spaceborne satellites, they are usually they sit above 600 kilometers, and 300. Some LEO satellites are also happen to be around at 300 kilometers. So roughly we can say about 300 kilometers are the spaceborne satellites. Then lower to that is HAPS, which is high altitude platforms. They're also called as balloons or airships. So they sit above at around 20 kilometers distance, and then your UAVs and drones, they they can't go beyond. So here it's 150 meter, but conservatively you can call it like 500 meter to 1000 meters. You can't go beyond that. Now, Bharat 6G vision also highlights the importance of NTS. That's why I've kept this slide that whatever we are discussing, it potential to be deployed in 6G, and it is active area of research. If you're interested in doing research in any of this domain, you can think about it because it's an emerging area, and our government is also pushing into this area. So as you can see, all these snippets they are taken from this again Bharat 6G vision document. They have explicitly talk about how this they have provided their vision, how there will be a connections between different satellites and how they can provide the ubiquitous connectivity to the Earth. And this is also a interconnected uh, network, also called as multi-layered architecture, where your satellite is connected to a HAP, which is also connected to the base station on the ground, and then also with the drones. And these are some applications. For example, satellite can provide connectivity in the desert area or the sea area, right? And then they in turn can be connected to the satellites and then provide the services on the. Now we'll talk about them individually, all these platforms. So first is UAVs, also called as UAS or more popularly as drones. So what are the pros and cons of them? So the pros of UAVs are they can fly at low altitude, as low as 50 meters and as high as 1000 meters. They are highly flexible. The flexibility is high. You can maneuver them easily, and then on demand we can deploy. These are some pros, but the cons are also significant. For example, This is one of the most important concern with the UAVs, that they have high propulsion energy. What does this mean? In order for UAV to operate, it has to hover at a certain, and most of the energy to make your UAV afloat in the air, it goes into the propulsion blade consumption. For example, if you have 100 watt of energy, just for example, 100 watt is anyway too much. But if, just to put this in perspective, if you have 100 watt of power at UAV, around 60-70 watt of it will go into just keeping the operation of UAV, making it afloat in the air. This is very significant, and then you will just left with very less amount of power, left amount of power to do other tasks. And since it is not flying at very high altitude, the coverage umbrella is also small. So if it is to be used for providing the coverage to the ground, then it can cover only few 100 meters or at most few kilometers, not more than that. Coming to apps, their pro include quick deployment. For example, these pictures you can see, there are some project from, one is from Thales Alenia, and these are from Google Loon. Google has also launched it in around 15 or so, I guess. And then I think Amazon was also into this briefly. So these are apps, so they can be deployed quickly. So they are, you can think of them either as a bigger aeroplane or a balloon with hot air in them, so that they can stay in the air above 20 kilometer, and then we can deploy certain energy harvesting or solar panels, which can keep powering them, and then you can use it for further connectivity. There are also tethered based balloons where there is a tethered connection. So this is not as popular as, and we might not have seen them in practice. As to the satellite and UAVs, they are getting popular with each passing day. Now, another pro with apps are they can cover larger geographical area compared to, because they are very high in the sky. They're sitting at 20 kilometers, talking about 20 kilometers height. Now their energy consumption is very low because they are mostly static. They don't have this chopper-like plates which are to make it afloat. So they are mostly with this hot air, and therefore the consumption of energy is very low. They also have, since the size of it is large, we can just plant the solar-based panels on them, so they can harvest the energy from sunlight. And the cons include the stabilization, because at this high altitude, the stability is important, severe weather conditions, and then refueling if they are not solar. So we can't just rely on the solar-based panels. So they are just solar-based just to just support, complement the fuel-based fuels. So therefore, the refueling is difficult. It's not like you can just pull them on the ground and then refuel it and then again leave it in the air. So that's a cons for it. Coming to the satellite. So satellite Geo and Leo, Geo, Meo and Leo. So Geo, we have been using it for very long time, and for our GPS is mostly based on our Geo satellites, and the TVs, satellite TVs are also based on. The pro of Geo includes the huge coverage. So ideally, just three Geo satellites can cover the entire Earth surface. Right? Just three satellites, because one satellite can cover roughly 120 degree. If you consider the beam width 120 degree, then we just ideally need three satellites to cover the entire. But the cons of it is huge delay, since it is sitting above 6,000 kilometers distance away from the Earth's surface. It causes huge delays, and that in turn translate to attenuation. And then because of this, the capacity gets saturated. So there is only limited capacity you can achieve on the ground. Those are cons of LEO satellites. Coming to MEO and LEO, they can also provide large coverage but relatively lower than LEO. And their cons include the non-station. So basically, LEO satellite, the orbit in which they operate, they can't work standalone. Just to keep them in orbit, they usually work in constellations. And if we talk about this NTN frequency, as you can see, these are certain frequency bands of satellites. So it ranges from 1 gigahertz to 40 gigahertz, and these are different application in those frequency. Okay, so this is basically the satellite frequency band. The wavelength ranges from 10 centimeter to 1 centimeter. So this also covers millimeter frequency band. Millimeter frequency band, if you remember, that's also a 5G frequency band, about 24 gigahertz. So this K band, or rather just a K band and Ka band, it overlaps with the 5G frequency band. Therefore, there is a lot of research ongoing in studying this integrated terrestrial and non-terrestrial. Now, in this slide, just to show you how many satellites are hovering above the Earth's surface, to see all these are these dots, seeing they are the satellites. This color coding shows the satellites from different countries. This blue satellites, they are from USA, orange ones are from Russia, and this yellow satellites, lot of them are from India. Our space agency, ISRO, has also launched. Now, these are some terms which are from the standardized, not as a layman. What terms do we use in standard? So, standard, by standard, I mean the 3GPP or IEEE. These are standardization bodies. So, they define it with different terms. So, first is service link. So, the service link is the radio access provided to the UG. So, and this is also referred as radio interface, UU interface. It is in 3G. So these documents, by the way, they are free to read. You can just go through 3GPP websites, and therein you can find. So release 17, in release 17, if you type on Google release 17 3GPP, you can find the discussion on NTN. So there with release 17, I think they talked about this NTN over 5G, how we can integrate non-terrestrial network with the 5G. Next is SRI interface, or also called as feeder link. So feeder link is basically the connection between satellite in the sky and a earth station on the ground. So that earth station on the ground is called as gateway. So basically the feeder link is the connection between the satellite and the gateway on the ground. So it provides the gate for the terrestrial infrastructure. And GNB is the next generation node B. So the base station, that's nothing but a base station. In 5G terms and the standard terms, for example, the towers which you see, in layman terms, we call them towers and or base stations. But as an engineer, as an electronics and communication engineer, we talk technically. So in technical terms, from standardization perspective, those nodes are called as GNB. And these nodes in 4G were called as ENB, enhanced node. But with 5G, we are calling them GNB. Then SNB is the counterpart in the space. If satellite works as a base station, then is SNB. 5GC is the 5G core network. So all of the data, it routes through the core network, which in turn then connect it to the internet. And gateway, we've already seen the gateway, which are just those dishes on the ground, you might have seen it, which receives the satellite signals. And then UE is user equipment. User equipment is your mobile end user device, end user terminal. they are called as UE. And VSAT is the UE for satellites. So it stands for very small aperture terminal. It's basically a smallest uh, user terminal, which can receive the satellite signal. So this is more relevant for receiving the satellite signal, and UE is our mobile signals, our mobile phones. Now, there are three possible types of UEs, that is user equipments. So one could be UEs that are capable of accessing only terrestrial 5G, that is terrestrial network. And then there can be UEs which can exclusively access just NTN. For example, your VSAT. And then UEs which can receive the signals from both satellites and the ground. iPhone 16 can receive the signals from your 5G base station or GNB and also from the satellite. And broadly, we can just categorize also them in terms of these two categorization. One is handheld, whichever we can held in hand. Those are also called as handheld UV. And UVs which are mostly stationary, they don't move around. They're also referred as VSAT. Okay, so they are stationary, they can't move around, and we just mount them permanently somewhere, like vehicles or the airplanes, and then they receive the signal from the satellites. And these are some technical requirements of this VSATs and handheld devices. You can refer them if you want. Next is there are broadly different use cases. One is FSS, fixed satellite services. Another is BSS, broadcast satellite services, or TV, and it uses the standard DVB-S2. And then mobile satellite services, which we are not using prolifically, but maybe in future down the line we'll use it. Now, these are certain architectures. Architecture as in what is the possible network topology or an architecture which can facilitate the use of this NTN with TN, or just how can we use this NTN to provide the service to UE, that is end users. Ultimately, end user is your UE, whether it's handheld or VSAT, doesn't matter, but it's a UE. How we can use these NTNs. So these architectures basically provide. So these are the architectures taken from our own work. So we have published a very nice survey with this name Evolution of Non-Terrestrial Networks in 2020. So one possible architecture is we can use this non-terrestrial platform, which could include satellite, your UAV, satellite, and as well as UAV. Okay, so in this, your NT platform basically is acting as a and these links you can see this link between satellite and this gateway on the ground is called as feeder link, and this base station to the end user it's called as service link. So these are all service links. So in this case, U is acting, anti-platform is acting as a user. So therefore, this end link is called as service. So this is being serviced. So we are servicing this UAVs or the satellites. And therefore, in this particular architecture, they are called as user. And there is your code network, which is connecting to the data network and to the internet. Another architecture is anti-platform. They can be used as backhauling. So backhauling means, for example, the your GNBs, the base stations, all of them are connected to the wired link, that is optical fibers. When we communicate as a user, the data goes to the nearest base station, right? And that connection is wireless. It is called as front haul. So this data exchange between UE and the base station is usually wireless, as we know it. But how these base stations they communicate together usually there are underlying fiber cables. All of the world is connected with the fiber links. Because in wireless medium, you cannot transmit large amount of data. And the base station, these bigger base stations, they're getting data from lakhs of users. So, and then there's those base stations to exchange the data between these base stations. They're all connected through the fiber links. So that fiber is called as back. That connection is called as the backhaul connection, which is happening at the back of this whole network. So in this particular case, when these two base stations, for example, if because of geography, if you're not able to lay fiber between them, then you can deploy some NTN node in between to set up a backhaul. That is another possible use case or architecture. Another is NT platform will act as a relay for the end user. So in this case, there is no direct connection between your GNB and the UE. Then you can deploy an NTN to relay the information. And last but not the least is NT platform itself is acting as a base station, okay? And which is providing the services to the directly to the user. And this is another backhauling connection between the NTN components. And then ultimately for connecting it to the internet, it goes through the ground network gateway through feeder link, which is connected to the core network and then eventually to the data network. So these are some possible architectures. This is by no means exhaustive, but broadly it will capture all types of architectures. And for architecture, from satellite perspective, there are two different types of load. Architecture defined in terms of payload. So one is called as transparent payload architecture and another is called as regenerative payload architecture. So transparent payload architecture, it's nothing, it behaves like a bent pipe. So there is no active operation happening at the satellite. If you transmit something, and imagine if you have a bent pipe here. So this pipe is just bent. So whatever goes in, it simply leaves out. So in this type of architecture with transparent payload or bent pipe payload, there is no processing capabilities at the satellite. It's just acting as a bent pipe. Okay. The dead so if you read this, so it has no onboard processing capabilities that can change frequency carrier of the received updates, filter and amplifies before transmitting another data. So it simply filters and amplifies before transmitting. That's the simple operation. It is just filtering and amplification. Now the disadvantage of this is since it is not processing it effectively, so when it does amplification, then in the process noise also gets amplified. We are not also deploying any security based protocol and therefore it is also vulnerable to security attack. And since it is not actively managing, then we cannot establish ISL connections. ISL connections are nothing but inter-satellite links. The counterpart of this regenerative payload, just to you can think of this as a base station sitting on a satellite. That's why it is called as regenerative. It's regenerating the whole signal. So whatever capability base station has, the same thing can be replicated on the satellite. The satellite has all those functionalities same as GNB, then it is a regenerative payload architecture. And all these interfaces we discussed previously, it's called as UU interface, NGC interface, and NG6 interface. These are different orbits of the satellites. And these are some technical parameters and the supporting applications corresponding. You don't have to go into the detail of it, but just for completeness, I have just given it. So we'll mostly these are also satellite related stuff. So later on we'll focus on the UAV aspects. So if you combine them, all the NTN with the TN. So the resulting, this is what we have proposed, that all of them can form a multi-layer architecture, wherein your NTN component with satellites in all types of satellites, along with UAVs and apps, along with terrestrial network, they can form a multi-layers. This is layer one, layer two, and layer three. You can think that first is space segment, another is air segment, and another is ground segment. So if we can use them effectively in a cooperative manner, then it can give rise to many new applications, and it will solve a lot of problems related to connectivity issues. So therefore, this NTN, they are crucial and critical in bridging that gap, 50% of internet penetration. So only with the help of NTN we can achieve that. Otherwise, without NTN, it's not possible. And these are various use cases which are possible with uh, type of multi-layer architectures. And for example, aerial telepresence, this computing convergence, ubiquitous internet, pervasive internet, all these are, maybe you might be familiar with many of these use cases. So these are basically the applications which are possible when we can seamlessly integrate all the different layers. And the satellites will have different type of coverage area depending on their orbit. For example, geo, usually their coverage area spans from 200 to 1000 kilometers. Non-geo includes 100 to 500 kilometers, which include both your MEO and LEO. And aerial platforms, including UAVs and HAPS, they can at the most cover 200 kilometers, that too with HAPS. But with drones and UAVs, it is limited up to few kilometers. That's all. And these are some dedicated frequency band which are listed in the standard. So this is from, for example, if you search this 3GPP TS38.101. So this is technical, TS stand for technical specification document. So this is from release 17 and release 18. So they have specified different frequency band for uplink operations and the downlink operations. Now there are two common questions when it comes to NTN. So whatever NTN which we are envisioning for 6G, will they differ too much from TN, that is terrestrial network? So basically NTN, as I also indicated earlier, they will be just complementing the terrestrial network. So you can't just discard the terrestrial infrastructure and rely solely on the NTN. They'll just act as a complement. For example, if we are not able to reach a certain geographical location, then in those cases we will use NTN, but otherwise it cannot compete with terrestrial network. Because terrestrial, we don't have limitations of space, we don't have spatial limitations of the power. But in space, if you want to deploy this, we have limitations of space, because satellites you can't just make it as big as a base station. Just given the swap constraints, that is size, weight, and placement, then those are the difficulties. And what about the existing satellites? For example, if you're talking, if we want to use the existing satellites for our terrestrial connectivity, can we use them? It depends on the application. For example, if it's a regenerative payload architecture, then we cannot use the existing satellites which are already there. Then we need new satellite launches to make them capable of all these functionality. But for transparent payload architectures, yes, we can use the existing satellites. So why are we talking about NTN now? Why not we have used them before? So previously there were various challenges. For example, the cost of launching the rockets was very high, the satellites was all very high. But now the situation has changed. When the governments have allowed the private sectors to come into this field, initially this business was kept to the government itself. So the private operators, they were not allowed to participate in this type of businesses. But now the government has opened this for private players, and therefore a lot of development is happening. For example, the SpaceX, which is the famous company from Elon Musk, they have launched thousands of satellites, LEO satellites, and mostly their internet is based on the satellite. They've also launched the satellite-based internet connectivity, broadband services in India also. So therefore, because of this changed situation, this NTN has become into the. Now, this standardization timeline, we have briefly discussed that when we are anticipating this 6G, but maybe these are different aspects. For example, this study items was related to this 15. Then there was talk about the satellite access in 5G. So, as I highlighted with release 17, the exist with evolution of 5G, we have talked about how we can use the satellite with 5G. And 2030 is the expected timeline when we can expect the 6G to be commercially deployed. And these are certain challenges. Okay, so first is large distance. Because of large distance, high path loss, the propagation delay, and because of the mobility of the satellite, it creates different problems. And then spectrum coexistence with the terrestrial network, and this is another challenge. Direct to handle access, because the attenuation is very high. So how will you design the antennas, or how can you capture and amplify so weak signals in smaller devices? Now we'll focus our attention to the UAVs, which is one of the NTN components. Okay, so before moving further, I would like to take 5-7 minutes of break, and then we'll start again. Is it fine, Nageshwar?